Okay, so for this question, they say if y equals to 3x minus 2 times with x plus 2 squared, so this is a polynomial function, supposedly, find x and y intercept. So for part B, to find x intercept means we have to let y equals to 0. Find out what is your value of the x. So therefore, 3x minus 2, x plus 2 squared will be equal to 0. So in this kind of case, you can see it already in factor form. It means that x plus 2, x plus 2. So you will have your x as 2 over 3, x equals to negative 2. So your x intercept there are x equals to 2 over 3 and negative 2. So meanwhile for your y-intercept we let x equals to 0. Find out your y. So 3 times 0 minus 2, then 0 plus 2 squared, find out. It is equals to negative 8. My intercept is y equals to negative 8. So go for question B. So what is the purpose? You can see the question, actually they are related. They ask you to find intercept. They ask you to find extremum point. What means extremum point here? Means find out our maximum or minimum if possible. Alright, then C ask us to find inflection point. Actually, we use all this information for the part C, sketch the graph. Alright, so we go for extremum point. Before we can get extremum point, we have to get critical point first. Alright, you get critical point first, then you do the test to verify whether it's maximum or minimum. So that is the procedure. So to find critical point, you have to differentiate the function, differentiate the polynomial here. So differentiate this dy dx dy dx. So you differentiate your y respect to x, you can see your x in product form. In front here a linear, at the back here also a linear in power, right? So product rule. So how to use your product rule? Salin depan, differentiate belakang, plus salin yang belakang, differentiate depan. So when you differentiate at the back here, the function at the back here means we only focus for x plus 2 and square. So in the bracket of square, when we want to differentiate this, means we use power rule. Because of x in something bracket and power. So power rule, power turun depan, power tolak 1, differentiate dalam kurungan 1. Then differentiate yang depan pula, we focus this one, 3x minus 2. So we differentiate 3x, we get 3. We differentiate negative 2, we get 0. So how to simplify this? We have to simplify and let it 0 to find out critical. So in order to simplify, we find out the common factor. You see, this is our front part, this is another part. So you see the common factor, you see the bracket, they're having the same x plus 2. So this common factor we can factorize out. Therefore, the remaining here will be 3x minus 2 times 2. So it will give you 6x minus 4. Continue. At the back here, when you take out one factor of x plus 2, you still remaining have 1. You still have 1 factor at here. So expand with 3, it will give you 3x plus 6. So simplify, where you can see 6x plus 3x, 9x. And the number negative 4 plus 6, 2. So we done our first derivative. To get critical point, we have to let dy dx equal to 0, which is x plus 2 and 9x plus 2 equals to 0. So they are in 12 factor form. So from here you can get directly critical number x equals to negative 2. Critical number, another one is negative 2 over 9. So once you get the critical number for the x, then we need your point, right? You want points, right? So we can find that what is your y coordinate. When x equals to negative 2, what's your y coordinate? Put that to the original function here. Put that, this is negative 2, this is negative 2. Try to calculate your y coordinate. So we can notice that this is 0. Another critical number, x equals to negative 2 over 9. What's your y? So we get our critical point or our stationary point. Negative 2 and 0, negative 2 over 9 and this one. But they haven't verified yet, so we can't determine it is maximum or minimum. So the next procedure is undergo the test. So we can do first derivative test or second derivative test. Either one to verify this stationary point whether it's maximum or minimum. So we look at our first derivative. If you want to use first derivative, look at the first derivative. Yes, we think for us it can be differentiated again. Quite easy to get second derivative, right? So we proceed to second derivative test. So we choose second derivative test to verify this point. So from dy dx, which are x plus 2 and 9x plus 2, where we can expand and we differentiate it again. It will be more easier instead of using product rule here. So expand it 9x squared plus 2x plus 18x plus 4. So actually our first derivative only in quadratic. So when we do second derivative, we differentiate one by one. 18x plus 20. So we test for the first point when x, the first critical number, x equals to negative 2, what's the d2y dx squared? What's the second derivative result? We substitute the x coordinate to get the value. The value here, negative 16. So this is the result. When we get negative 16, you have to come up conclusion. What does it mean? From second derivative is talking about concavity. If positive, concave outward. Negative, concave downward. So we get negative value. So you have to come out the conclusion. Where this is less than 0, it has concavity downward. So we can verify this is maximum case. Alright, so you must have your result and conclusion. Then we repeat for another critical number, negative 2/9. So it's positive 16. Our conclusion will be positive, will be concave outward. So this is minimum case. Therefore, we can do our conclusion here, where maximum point is fall on the x negative 2. Minimum point is negative 2/9 and negative 2048/243. So from critical point here or from stationary point here, we managed to classify it. It have a maximum and minimum. Then when we go for the part C, when they're asking inflection point. So when they're asking inflection point, we have to find from second derivative equals to 0, because from the first derivative, all the critical point here already classified as maximum and minimum. We can't find any inflection point from first derivative. So therefore, we continue with second derivative. So for d2x, d2y, d2x, d2y dx squared equals to 0. From here we find our inflection point. So your x here equals to negative 10/9. So you get your x, you find out what's your y coordinate. Substitute that into original function. So this point might be your inflection point, might be only. So if you want to verify it, you have to undergo the test again. Alright, so you have to undergo the test again to verify is it this one inflection point. So you can use first derivative or you can use second derivative. If you use first derivative, means you will analyze on the tangent, going up, or going down. If you use second derivative, you have to do your table, you have to observe the concavity change, up to down or down to up. Alright, so we do our test here. We can using our second derivative test. So I'm still using second derivative test. So find out your interval first. So your x is 4 on negative 10/9. Alright, your x is 4 on negative 10/9. And then, so let's say you take a value to test, means your interval, this one will be less than negative 10/9. This one will be more than negative 10/9. So we take a test value to put in second derivative. So that to see the concavity. So when you want to test a value, you have to be careful because you have other critical point. You have two critical points before this, right? So you have your x, you have your maximum minimum point. So if we rearrange the critical x here, you have -2, you have -2/9, now you have -10/9. So when you want to take a test value randomly, so you do over the interval. So you have to within the interval. So if you rearrange this from the smallest to the biggest, the smallest start with -2, then -10/9, then -2/9, correct? Correct. Then from these pointers now, from part A and part B, we know that when x equals to -2, here we have a maximum point. When x equals to -2/9, here we have a minimum point. So now we have a inflection point, maybe an inflection point for at -10/9. So when you want to test a value, so don't exceed -2. If you take too far, you are looking on concativity here. You are not looking the concativity here. So take a value in between, yes, less than -10/9, but not too far away. If you're too far away, the value fall in too far away, it will be another interval. You can't see what happened. It will be changes already. So -10/9, within -10/9 and -2, -1.5. Alright. So -10/9 within this one, -1 can. So we want to see the concativity before this part. The concativity before this point and concativity after this point, but not too far. Alright, so substitute this into our second derivative. We get positive or negative. When we substitute this, here will be positive, right? When we substitute this, negative. So I'm using second derivative test. So second derivative test, when you negative, concativity downward. Positive, concativity upwards. So for this point, before that, it concativity downward. After that, it concativity upwards. Means for this point, there definitely is a inflection point. So you can see the difference how we use second derivative to test stationary point to be maximum or minimum. How we use second derivative test to test on our inflection point to see the concativity change. Alright, so from here, we can conclude up. This point is inflection point. Then lastly, we sketch the graph. So with all these results, we know inflection point. Before that, -2 is maximum. So you just imagine you have 3 points here. We get a roughly idea. You have 3 points. You have 3 points. The -2, the left one, and the in middle, and the right. For this negative, it might be a maximum. For the middle that we found here, -10/9, it will be inflection. So for the last one, -2/9, that point, it will be a minimum. So your graph will be like curving like this. Alright, then we plot into our axis together with the intercept. With the intercept, we already count here. X-intercept means it might be undergo. What's your x-intercept? Y-intercept? What's your value at y-axis? Alright, so label it one by one. Draw it correctly according to the coordinate. If you're negative at left or down. So we take this. Plot all your graph, all your points, where it's supposed to be have maximum, minimum, intercept. So when you have -2, y, 0, this is maximum. At the same time, it is a x-intercept. Okay? So when you go for inflection point, it fall at -10/9. So all the points fall at negative part. So I adjust a bit. All our point all fall at negative part, so I adjust a bit. So we have 1, 2, 3, -2, 0. Maximum. And then -10, 9. Inflection. Then this one, minimum. Minimum -2/9. Okay. So let's say this is the most minimum point. So go up. Before the inflection point, concave downward. After inflection point, concave upward. Intercept at y -8. This minimum point, label, inflection point, and intercept one more. One more intercept fall on here, 2/3. Lastly, this is our curve. Y equals to So lastly, have a check. Did you label your y-axis? Did you label your x-axis? And every point here, 1 point. Second this one, inflection point. Third one, minimum point, x and y. Then y-intercept, x-intercept, and your curve. What's your name of your curve? So actually it's possible, we're going to write. Actually it's possible if you have enough space, you can write this point. What's your label? 10/9, -1024, 243. This one minimum, -2/9, -2048, 243.